Hello everyone, welcome to our poster, AR Game Traffic Characterization, a case of Pokemon Go in a Flash crowd event. This is what motivated us to take the research. To realize AR in real time, we need mobile devices such as smartphones to sense the environment. This sensing data needs to go to the edge or backend server, and the inference result will then come back to its mobile devices so that virtual objects can be rendered at the right place and right angle. This process takes time and needs high bandwidth, so the delay and bandwidth consumption are big issues. To know how latency and bandwidth are like, we go out to investigate Pokemon Go in real life. We recorded the game traffic from 6 volunteers in the Safari Zone event, which had approximately 890K visitors over the 4-day span. The challenge of collecting packet traces in the wild is the diversity and level of manipulation required to the volunteers' smartphones. For Android phones, routing is required to install a packet sniffer. For iPhones, routing can be avoided, but a macOS device is required to set up a virtual tunnel to the phone. To avoid all these burdens, we need a platform-independent and manipulation-free approach. In that, the volunteers' phones are connected to a LTE hub served on encrypted Wi-Fi. This measurement was taken on a laptop connected also to the Wi-Fi subnet. The TCP dump process ran on a laptop and saved all packets passing through the subnet. After the event, about 160K packets were recorded, and 43% of them were Pokemon Go traffic.
Through analyzing the recorded packets, we noticed that the startup traffic is much larger than the steady-state traffic. This is because for players who are new to the playground, information such as the area map and cached user data need to be updated before the game session can begin. The average uplink and downlink bandwidth are 3.27 and 7.57 kbps per player in the startup state, with a peak downlink demand of 17 kbps. In the steady state, there are only 0.6 and 1.48 kbps per player, with a peak downlink demand at about 6 kbps. The bandwidth requirement is higher than the conventional online games, but similar to other mobile games. The mass majority of the RTTs are short. About 80% of the RTTs are less than 100 milliseconds, and about 45% of them are within 10 milliseconds. For most players, it feels like the server responds in real time for most part of the event. This suggests that the server is well situated and very close to the clients. When the traffic load is light, the network delay is negligible. However, the long RTTs are extremely long. This is very likely the result of network saturation. In these cases, the buffering and retransmission delay are substantially long and dominate the end-to-end delay. The figure shows the cumulative distributions of RTT and startup and steady state in log scale. We can see here that the volume of the startup traffic plays a role prolonging RTTs. 29.7% of the RTTs are within 10 milliseconds in the startup traffic and 48.5% in the steady state traffic. We also see here that the longer RTTs are not stretched as much by the startup traffic. The difference in the CDFs is larger at shorter RTTs and smaller at longer RTTs. The difference as a percentage is 18.8% at 10 milliseconds and 8% at 200 milliseconds. The large difference in the CDFs at 10 milliseconds suggests that the volume of the startup traffic adds to the delay. The much smaller difference at 200 milliseconds indicates that despite the high volume, the startup traffic is not the main cause of the extremely long RTTs. Throughout the measurement, the volunteers play in a group nearby the data logger. Their similar or even synchronized actions playing the game causes traffic concentration, and this traffic concentration might be the root cause that impairs the gaming experience. So to conclude, there are two major findings and possible suggestions. First of all, network delay varies significantly. To mitigate this effect, we might need an offloading mechanism to meet the end-to-end latency budget. Second, the traffic volume and traffic concentration impact network delay. Additional compression and randomization schemes might help deal with this problem. Moving on, our plan is to expand the data collection and analysis effort to gain more insights to AR app design and to create a traffic model or user model to realistically evaluate the operation of the AR app.